Hello everyone, welcome to the 6th lab of the semester where we will be continuing our discussion of transistors, and in this experiment we will be building a small signal amplifier. So let's talk about it. So a small signal amplifier does just that. It takes some small input signal and through the use of our transistor and a clever configuration of resistors, it gives us a boosted or amplified output signal. This circuit is going to be split up into AC components and DC components. So our input signal is the AC signal that we're interested in boosting. But in order to do that, we need to prime our transistor so that it can actually amplify that signal. So what we have right here is just the DC portion of our circuit, and I will talk about it first. So what do I mean when I say that the transistor needs to be primed? Our transistor is just an electronic switch, and when a certain voltage is applied to our base, it allows current to flow from our collector to our emitter, which is going to be our output signal. So there needs to be some certain threshold voltage that, when applied, allows this transistor to be in the on state. And that is exactly what our power supply is doing. Our transistor usually has to have this voltage between this voltage drop from our base to emitter of around 0.7 volts is usually the standard, or at least it needs to reach that threshold in order to be in this on state. In this case, we have our DC power supply up here, and as current flows down, these two resistors are acting like a potential divider or a voltage divider. In this lab, our power supply is going to be around 20 volts, and these two resistors are chosen in such a way that when we measure our voltage at the base, then we should see that it's around this, at least at this 0.7 volt potential difference. Because when we look at our AC signal, well, in this lab, our AC signal is going to be around 100 millivolts. So when we look at our signal coming into our base, it's going to be our DC signal, our DC current, this minimum 0.7 volt signal, plus our AC signal. So it's going to be our tiny little oscillating signal offset up so that it's enough to kind of turn this transistor into its on state. So that's what these resistors on this left are doing. The collector resistor and the emitter resistor are just regulating the current going from collector to emitter. So one thing about our transistor is that we are taking this relatively small current going in and we're making it into a larger current out here. So one thing that we're interested in is this beta, or kind of also known as like the gain of our transistor, or the gain in our signal. And this is, we've talked about gain before. It's just the ratio of our output to our input signal. So in this case, we're going to find the collector current and our base current. So that is what our beta is going to be. So it should be something, relatively high, maybe around 100. It's a unitless thing because it's current over current. Okay, so that's one thing that we're going to be finding. It's going to be characterizing how much our signal is being boosted. One final thing that I wanted to talk about are these two capacitors that we have in this circuit. So these two are isolating our AC signal from our DC signal. I guess more so, really, it's preventing our DC signal from going into where our input and our output signal is. Because as capacitors do for DC signals, it prevents current to flow in this direction because charge will build up, but it'll allow AC signals to travel right through. So that's all that they're doing. They're just isolating our input and our output from our DC signal, because we're only interested in our DC signal being in here. Okay, I think that's about everything that I wanted to discuss. Now let's bring out the full circuit and talk about our inputs and our outputs. So this is the full circuit diagram, the one that we will be building in this lab. You can see over here, this will be our AC signal from our function generator. That'll go into our base. And over here, this is where we will be measuring our output, our V out, over this load resistor. And because our current is being boosted, this will just, this is a large resistor that accounts for that increased current. And down here, this is what we call the bypass capacitor. So if we have an AC signal coming in, the capacitor is essentially acting like a short, so it will bypass this resistor, or the emitter resistor, just going through the capacitor instead, and this will increase the gain of our signal. And this R gain resistor is a variable resistor, the potentiometer on our circuit board, which I will show later, but essentially it's a variable resistor, and basically it's something that we can adjust, and we will see how adjusting this resistor changes the gain of our signal. Okay, I think that is about it. Let's measure our components and start building the circuit. Let's start by measuring our components in step 1. Here is our R1, which is a 100 kilo ohm resistor, R2, which is a 10 kilo ohm resistor, RC, which is a 22 kilo ohm resistor, and RE, which is a 2.2 kilo ohm resistor. And on the left we have our C1, which is our 0.01 microfarad capacitor, and C2, which is our 0.1 microfarad capacitor. Okay, so let's turn this on and measure these components. Okay, so for the 100 kilo ohm resistor, we are measuring 100.0 kilo ohms, 0.1. I guess we'll call it 100.1. Okay, pretty good. Now for R2, looks like 9.88 kilo ohms. Okay. Now for RC, (21.89 kilo ohms). Okay, and here is the last one. RE is 2.139 kilo ohms. Okay, let's measure the capacitors. This should be C1, or yes, capacitors. Okay, switch it to measure capacitance. Okay, we'll call it 10.94 nanofarads, which is 0.0109. No, it's jumping up again. What is happening? All right, it's going back down. All right, yeah, so we'll call it 0.01098 microfarads for C1. Let's measure our C2. Okay, so we're measuring around, so this is 100.1.2. All right, we will call it 101 nanofarads, or 0.1001 microfarads. All right, so those are our measurements for our components. Let's build the circuit. So I have gone ahead and built the circuit from figure 3. And before everything is hooked up and I have all the wires connected, or the probes and everything measured to it, I figured I'd just go through the circuit and trace through the path. I did try to build it in such a way that it very much resembled the schematic in figure 3. So let's just go through it. Up here, I will have the power supply connected, and it will be jumped down to this row where it will fork. Let's go to the left first. So this is our R1 resistor, R100K. Goes down here to this row where I have a wire jumping it down here, where we have this 4-way fork where it is either jumped over here to the right, where it goes to the base of our transistor, or to the left, which is the C1 capacitor. Again, right now I don't have anything attached in. Eventually it'll be our input when we want to do our AC small signal boost, but right now the capacitor is in right there, but I mean essentially it's a dead end on the circuit. Nothing's going to, if current does flow, I mean eventually it has nowhere else to go. So it's more or less our capacitors don't do anything in this circuit right now. But since all we're doing is a DC analysis, that's okay. So let's continue on. Then it continues down to here, to this row where it goes through, the current can go through our R2 resistor, and then eventually down to ground. Okay, on the right fork we have our R3, our RC resistor going down here to our transistor, and just to, I guess I'll slightly pull this out. So we see that all 3 tines are on different rows, so they're all isolated. So we have our collector on top, our base in the middle, and our emitter on the bottom. And so we've already talked about the base. So the emitter comes out down to this RE, or our emitter resistor, and then to ground. Okay, and I guess just to zoom out, eventually, in this next part, we will, once we finish our DC analysis, we're going to be using this potentiometer, which I'm not sure if we've used yet in a video, but essentially it's a variable resistor, and it's a 10K resistor, so as we use this dial, it'll change the resistance of our resistor. So eventually, this is going to be hooked into our circuit, and I'll be measuring this, but just to see it. Okay, perfect. Now let's go ahead and attach our power supply and make our measurements. Let's start making the measurements for our step 2. I have my multimeter right here. I have gone ahead, let me show you all. I've attached the power supply. I've set it to 20 volts, and I've set the current limit to 10 milliamps as per the instructions. You can see that we're pulling maybe between, less than a milliamp of current through our circuit. So let's go ahead and make the measurements. So looking at step 2, we need to measure the voltage drop from our base, our collector, from our emitter, and then the voltage drop between from our collector to our emitter, so that would be our VCE. So let's find VB. So here, you can see that I have my little wires connected in from our probe, so I can just stick it into the circuit. And I guess I should turn it on. All right, so I will have the black lead connected to ground, and I will just be plugging in the other one into where I need it. So our first one is to find our voltage drop from the base, so that would be this row. So I'm actually just going to stick it in this row, same row, but behind the collector, or behind the transistor. Okay, so we are measuring a voltage of 1.751 volts for VB. Now let's measure the voltage drop from the collector. So VC, we are seeing 8.9596. I'll leave it up to you to put down which number you want. And then finally, voltage from the emitter, or VE, which is there. Okay. 1.093 volts. All right. So now, those are our top three measurements. Let's measure the voltage drop from the collector to the emitter. So I'm going to try to fit in. It's kind of hard to see, but you can have the positive, or the red, on the collector row, and I have the black on the emitter row. So this should measure the voltage drop from one to the other. And we're getting 7.88. Okay. Now let's measure our current. So to measure our currents, we're going to have to break our circuit and attach our multimeter in line with it. So let's first find the current going into our collector. So what we need to do is, that's the current coming in to here. I misplaced my pencil. That's fine. Okay, so what we can do is we can take out this resistor, connect our positive lead to it, and then so now current is going to be flowing through our multimeter, and we'll complete the circuit by putting in this black lead where the resistor was initially attached to. So the current going into the collector is 503 microamps, or 0.503 milliamps. And just to show you, I'm on the microamp scale, but I'm just getting I was about to say I'm getting better resolution at the microamp scale, but I'm getting it just died. So all right, so you can see you get better resolution if you're using these smaller scale. Okay, so 500 or 0.503 milliamps if we convert. Cool. Now let's attach our resistor back in. Do the same thing for our emitter. So what I can do is I can take out this resistor. I can attach my negative lead to it, and then attach in my positive lead where the resistor used to be. So we're seeing an emitter current of 0.3554 milliamps. Okay, so that's that. Let me attach this back in. Okay, so in your lab manual, it asks to subtract the two currents to find the base current, but I think it's a bit more accurate just to measure our current going into the base of the transistor just with our multimeter. So rather than, you can see in the manual it says to IB is equal to IC minus IE. Instead, we're just going to use this value that I'm about to measure here. So again, I've undone this resistor. I'm sorry, undone this brown wire, and I'm going to attach my multimeter in series with it. Okay, it's 5.6 microamps or 0.0056 milliamps. All right, so that concludes the measurement part of our DC analysis. You can calculate the beta of our transistor from our two measurements, and then in step 3 you can calculate the transconductance and the R G sub m and the R sub pi, which is the internal resistance of our transistor. And you can look previously in the lab manual to find those equations. Just to remind you about the transconductance, the G sub m, that is our current of our going into our collector over the V sub t. If you look at, well, I think it's equation 40 in the manual. And it just says in that line right below it that the thermal, V sub t is our thermal voltage, which we are taking the approximation that it is around 26 millivolts. So you can use that value for that calculation. All right. So now in step 4, we are asked to construct the circuit in figure 4. So we are adding in the AC components to create our small signal amplifier. So with those, we need to measure what those values are for those new components that we're going to be adding. So I will go ahead and do that now and then switch over to the completed circuit. So one of the things that we're adding is this smoothing capacitor, which is a polarized 10 microfarad capacitor. Yeah, that's if you look at the manual and what's written on the figure. So let's measuring amps. Sorry. There we go. Let's go ahead and measure the RC3 capacitor. And it looks like 9.72 microfarads. So close. We are also going to be adding a load resistor, which is a 1 mega ohm resistor. So that's going to be this one. So let's add, or let's measure this. You happy about that? How about that? All right, there we go. So we are reading 0.984 mega ohms. Okay. And finally, going back to this variable resistor that I talked about earlier, this potentiometer, we're going to be using this to as our gain resistor. So if you look actually in step 5, it asks us to measure the maximum and minimum, or it asks us to measure the maximum value of this resistor, but eventually we will need the minimum value too. So I'm going to go ahead and measure both. Let me go ahead and attach the leads. And we can see, so right now it's measuring 0.468 kiloohms. And as I turn this dial, you can see that the resistance goes up all the way to a maximum of 9.51. So our maximal, in step 5, this R sub G max, or our maximal gain resistor value is going to be 9.51 kiloohms, and our minimum resistance value is going to be 0.468 kiloohms. Okay, so now that that is done, let's build the circuit. So I have completed building the circuit from figure 4, and I again have tried to build it in such a way that it mostly resembles how it's depicted in the schematic. So let's go through the additions. Well, first off, the DC section really hasn't changed. We still have our positive and negative leads from our power supply. This is still ground. But now we have our input from our AC signal, the one generated by our function generator. So this is going to be our small signal, which will then, of course, be amplified, and we'll be measuring that. But right here is the input from our function generator, and it's in the same row as our C1 capacitor. So it's going to be going through, and eventually it'll make its way to ground. And you can see the negative lead from our function generator is down here on our grounding row. Okay, so let's talk about the C2 capacitor. So now we've added this load resistor, which is in the same row with our C2 capacitor, and eventually it just goes down to ground. And you can see the probes for our oscilloscope. So this is how we're going to be measuring our output signal, the signal that's going to be amplified from our function generator. We're measuring it over our load resistor. So this will be our channel 2, our blue channel. All right, and then the last part is this, our gain resistor and capacitor that we just put in. So we can see down here in the figure that the gain resistor kind of forks with the RE resistor, and so it's on the same row, and this long wire connects over to our potentiometer, and then current goes through that resistor, and then it'll come back up to here to where our C3 capacitor is, and eventually go to ground. So it was easier to have it over here. But those are the additions. So now let's go through the analysis of our circuit. So now that everything is set up, let's go ahead and move on to step 6, where we are asked to set an input signal of 100 millivolts peak to peak, so a very tiny signal at 10 kilohertz, and let's see what happens. So our channel 1 will be our input signal, and our channel 2 is right now measuring the V out, so over our load resistor. We'll change that up in a little bit. So let's just have a quick look. So for channel 1, our peak to peak, if you can see it, we are getting something around 100 millivolts, so between 104 and 108, around there. It's kind of bouncing around. It's a very small signal, so you can see it's kind of very noisy. And our output signal, what we're measuring over our load resistor, is at a 1.34 volts peak to peak. So we are seeing a roughly 10, we're amplifying our signal by by a factor of 10. And what's also noteworthy is that our output signal, when we're measuring over our load resistor, is completely out of phase with our input signal. So, okay. Looking at our manual, if we move on to part 8, we're now going to change around where our probe is at and measure the signals at different points in the circuit. So we have our VN, VB, VC, and Vout. And we are asked to represent this signal in equation form, where our voltage output, or our voltage, is amplitude times sine of 2 pi frequency times time, plus or minus our DC offset. So we're going to do this at various locations, and let's go ahead and get started. Okay, I wanted to zoom in on this section so that you all can clearly see the display of the oscilloscope. We can start making our measurements. So let's start with our VN signal. This is just the signal directly from our function generator, which should be close to 100 millivolts peak to peak at 10 kilohertz. And all of these waveforms are going to be at 10 kilohertz, so that's not changing. So one thing that our lab manual suggests is that we use the cursor feature to measure the values for our waveforms rather than the measuring tool of the oscilloscope. And I have them both displayed right now. I guess I already jumped to making the measurements, but you can see at this really tiny signal, because it gets kind of fuzzy. And actually, I've managed to clear it up slightly. This is kind of what it normally looks like. So let me fix it real quick. So it's a bit distorted, and it's not very accurate when it comes to the oscilloscope's measuring feature. Actually, you can even see it here. I'll show you. So right now it's measuring, it's kind of this fluctuating value. If I take this out, it jumps up even more to like 160 or something like that. So it's better to just use our other tool here. So what I've done is I've got the cursor, I'm measuring the voltage. I want to measure channel 1, and then this is shifting the location of the cursor itself. So I went ahead and put cursor A so that it lines up with the peak of our input signal. Actually, let me get rid of my channel 2 because we're not looking at it right now. And cursor B is lined up with the trough of our waveform. So you can see in the top left-hand corner that the delta V, which is the difference between our cursor A and cursor B values, is given. So this is the voltage difference between these 2 points. So if we take that's our essentially our peak to peak value. So even now, when we're measuring it here, we're getting 105 millivolts as opposed to the 112 which the oscilloscope is measuring on its own. And so this is our peak-to-peak voltage. So our true, or if we wanted to find the amplitude, well, that's just going to be half of our peak-to-peak voltage. So it's 105 millivolts, or 0.0525 volts for our amplitude. To get, and so the rest of the equation would be that value of the amplitude times sine 2 pi times 10,000 times t, our independent variable, plus our offset. And what exactly is our offset, or how are we going to find that? Well, again, these one thing that we can do is take our value that we have for our amplitude, because that's the the maximum distance from our point of oscillation. and we can add that to the lowest point that our waveform is at. So that would be our cursor B value. So if we add our negative 57.6 millivolts to our 52.5 millivolts of our amplitude, that will give us our DC offset. So let me see, negative 57.6 plus 52.5. That's just 5.1. So, or 0.0051, or negative 0.0051 volts is our DC offset for this input signal. Okay, let's move on to the next one. So this is the waveform at the base of the transistor. So what I've done is I'm going to be using channel 2. So that was originally measuring V out. So what I've done is attached a wire to the end of the probe, if you can see it, and just how I was measuring the voltage using the multimeter, I'm just kind of sticking it in the same row as the part of the transistor that I'd like to measure. So the base, and let's auto it. And just thinking, all right, so let's center it so that it's being displayed relative to the origin. So this is at 0 volts. And we can see that if the scale is 500 millivolts, that it's 1, 2, 3.5 high. So just looking at the offset, it's about 1.75, which is pretty consistent with what we were measuring the offset back when we were measuring the voltage at the base. It was like 1.751, I think. So that's a good sign. But if we want to actually measure the peak to peak, or the, by extension the amplitude, we kind of need to zoom in and get a better resolution on that waveform. So, but if we zoom in, it's going to be shifted up higher and higher. So I think probably 200 millivolts is. Actually, no, it's going to be small. So let's do 20 millivolts. And then now, if you can see in the bottom left-hand corner, I'm shifting everything down so that we can see our display. And so I need to shift it down, by this negative roughly 1.7, so that we can get the waveform fully displayed. Okay, so that's pretty good. Do we want to? I guess so. Let's stop. And cursors. Channel 2, good. And manual, yes. And so, oh, hello. Oh, I'm on track. I want manual. Thank you. And so this is cursor B. Okay, let's go to cursor A, shift that guy up. Okay, so that's pretty good. So our delta V is 113 millivolts. Our cursor B location is 1.6, cursor A is 1.71. So our amplitude in this case is 113 over 2, 60 or 56.5 volts. No, 56.5 millivolts, or 0.0565 volts. And so to find our offset, we will take that amplitude value, that half distance of our total waveform, and add it to our lowest point, which is the voltage at cursor B. So 1.6 volts plus our 0.0565 volts. So our DC offset in this case would be 1.6565. All right, so that's our procedure for these measurements. I we'll let you all make the measurements yourself and just kind of display them. All right, so now let's move on to 8C. So I'm changing the probe so that it's measuring the voltage at the collector, and let's re-auto it. Cool. All right, get rid of channel 1. Center it. So our scale, 5 volts. We know that from our previous measurements that our offset should be around 8.95, because that's what we measured on the multimeter. Okay, so if we want to zoom in, probably 200 millivolts is good, and then we want to shift down by 8 or 9 volts, so shifting down. Oh, perfect. Dang. Nice. All right, that's pretty good. Let's stop it. Cursors. Manual. Yes. That one up. Yeah, sure. Put this one down. Here. Yeah. I guess it's more accurate. Okay, so these can be our values. Delta V 1.35, value at cursor B 8.21, and cursor A is at 9.56. So you can get your amplitude and DC offset from those. And then now let's move on to finding our output. So I will put the probe back over the load resistor so we can measure our output. Auto it. Get rid of channel 1. So now, it's a bit wobbly. Sorry, I had to pause the video there for a second because one of my connections had gotten loose and wasn't giving me a good reading. So here we go. Cursors. Manual. Let's move it to right there, and we will move cursor this to like right. Okay, so go ahead and stop it. So this is our output signal. This is our boosted signal. And we can see that our peak-to-peak voltage is 1.34 volts, so it's roughly, what is that, 10 times larger, a little bit more. And then our offset is also very close to 0, since these two are close to the same value. But that is all for this section. You can make those calculations, and we can move on to part 9. So on to part 9, where we are asked to find the maximum value for Vout, and then by varying the frequency, we want to find the low and high cutoff frequencies. So very reminiscent of our bandpass and bandstop filters from our third lab. And I've gone ahead and kind of found our maximal frequency. And if you're looking at this bandpass, or essentially is a bandpass, our maximum value is it's a very wide peak, so it's kind of hard to key in on, especially just using the measure feature. So I went ahead and found it, and you can see that it doesn't change a lot. Here, I'll even show that as we vary our frequency, it really does want to stay around this value. So I believe in the previous section when we measured our Vout, I was seeing a delta V of 1.34, and I've only seen a difference of 1/100 of a volt. So I think we can say that, this is our maximum value. And then Eventually, we're going to want to find the gain, and to do that, we will need the ratio of our V out to our Vn, but I know that our Vn is really going to change or stay constant around this 105 millivolts, so we don't really have to worry about that. So if we wanted to find our high and low cutoff frequency, I mean, usually we would take the gain, divide it by the root 2, but instead, I'm just going to be taking the output voltage, maximum output voltage, and dividing by root 2 because our input voltage is staying constant. And so we should be looking for a value of around 0.955 volts peak to peak. And so what I can do, if I divide that number by 2 again, by 0.477, I can set my cursors, my cursors for, what's the closest we can get, 0.48727, I guess that's it. So that's going to be 960. Okay. And I can find the point at which this waveform kind of perfectly lines up with our values from our cursors, our markings. So I'm now going to find our low cutoff frequency. So I'm going to decrease our frequency until we start to see our blue waveform kind of line up with our 2 points where our cursor is at. Okay, getting close. Okay, and then I'm actually going to just increase this one just a hair. So what is that? That gives us a change in delta V of 0.952, and our actual value is 0.955, so that's even closer. All right, that's pretty good. You can't see the function generator, but maybe I'll actually zoom out in the feature ones. But actually, I guess I should. Let's just do that. It's the problem of wanting you to see both the value for our V out and show the function generator. So I've decreased the frequency, and I'm getting a low cutoff frequency of 1.850 hertz, so pretty low as far as our frequency is concerned. So that would be our low cutoff frequency. Now let's start increasing our frequency to find our high cutoff. So you can see that it spikes, and then it kind of stays at this value for a very long time, and then not until we start getting into the hundreds of thousands of hertz does it really want to come back down. Okay, we'll go ahead and decrease this. Okay. So I think that is about good, right there. So at 351 kilohertz, so 351,000 hertz, we are seeing the high cutoff frequency. Okay, I can zoom back in. And oh no, well, just so you can see, 351, and then you can see it gets pretty much lined up with our two values. Okay, and just out of curiosity, what are we measuring? So we're getting 960, 952, so I guess our measurement tool is kind of agreeing, we are getting agreement between our oscilloscope and our value. Okay, so that's part 9. Now for part 10, you can calculate the low cutoff frequency. In part 11, we are asked to find the gain in two different ways. So one, just by taking the ratio of our input and our output. So from our measurements, we have that our output value was 1.35 volts at its maximal, and then our input voltage was this 0.105 volts for our input. So I'll go ahead and do that calculation. So what was that, 1.35 over 0.105. Ooh, it's really zoomed in. So we have a gain based on our ratio of our two signals of 2.86. And then you can also calculate it using equation 10, which is in the manual. Okay, so that's it for the this part. Now we're going to repeat this process again, but for when our resistor, our gain resistor, is set to its minimum value. And if you remember back when I measured it, it was around, what was it, 468 ohms. So we're going to go through this process again with our minimum gain value for our resistor. All right. So I have re-autoed everything, and I'm displaying our input and our output signals. I just wanted to show you what happens when I change the potentiometer back to its minimum value. So let's take a look. So now it's at its maximum, and now I'm going to start to decrease it. And we can see that our input signal is staying the same, but our output signal is getting much larger. So I had to scale it back, zoom out so that the waveform could fit. It was previously at 200 millivolts, and now the scale is at 500 millivolts. So by decreasing the resistor, our gain resistor, we have our signal has been amplified even more. And so now we're going to run through our measurements and see how much and how everything's shifted. All right, let's start with 13, or step 13, part A. So A through D, we're doing the same thing where we're representing our input signal, our base, our collector, and our output signals as sine functions. All right, so I have set my function generator back to 10 kilohertz, just like it was in the previous section. You know, it is still 100 millivolts peak to peak, and I am now measuring the input signal. And I went ahead and aligned the cursors. So we are still seeing that our peak to peak voltage is 105 millivolts. Our value at cursor B is negative 58.4, and our value at the peak, cursor A, is 47.2 millivolts. So from these, you can calculate the amplitude. It's the same as it was in the previous section, and you can get the DC offset, again, by adding our value for the amplitude to our value of cursor B. Okay. Now, let's switch over to measuring channel 2. I have to get my wire again, so I'm attaching it to there. Let's auto it. And because we're not interested in channel 1 anymore, I'm actually just going to unselect it, so it won't show up again. Or I've just disconnected the probe. Okay, let's auto this. Okay, so scale is 500 millivolts. So again, our DC offset is around 1.75, which makes sense. So let us take a look. And it looks like our peak to peak is going to be roughly around 200. So I think we can set this one down to 20 millivolts again and start adjusting so that we can get all the way down there. So we need to shift down to negative 1.75 roughly. Oop, not that much. Okay, perfect. Cursors on, manual, channel 2. Ooh, look at that. So let's stop it. I almost hit auto again. I have a bad habit of doing that. So that's the top. That's the bottom. Yeah, let's do that. Okay, so there are our values. Delta V is 110 millivolts. Our cursor B is at positive 1.6 volts. Our cursor A is at positive 1.7. So the offset's the same, and our amplitude is going to be roughly the same. So this is still the unboosted signal. Okay, now that you have that, let's change to the collector. So this is the output of our, or this is how our signal is going to be boosted. Okay, so 5 volts. So just looking at this, if this is 5 volts, then our peak to peak is roughly going to be around 5 volts, if that's our scale. So if we wanted to scale it so that it's the entire thing, I would say maybe, I guess around 1 volt would be ideal. I think 500 would be too small. All right, so 1 volt, and then we need to shift down so that we are at 8. Perfect. So there's that. Let's go ahead and stop it. Cursors. Okay, so we are measuring and cursor B up. All right, that's fine. So we have an delta V of 5.4 volts. Our so you can get the amplitude. Our cursor B is at 6 volts, and our cursor A is at 11.4 volts. So you can find the DC offset again. Okay. Now let's find our signal, measure our signal at V out over our load resistor. So I've switched over the probe so that it's over the load resistor, and thankfully there's no more DC offset. And actually, I think we probably could use the measure feature to use it, but just to be consistent, I will continue using the cursor. Centered. Oh, that's kind of right on the money. Oops, wrong one. Okay. Okay, so we'll say that this is our values. I think I kind of have it lined up. So delta V is 5.4, and then our cursor A and cursor B are at negative 2.72 and 2.68 respectively. So from those, you can again answer, you can put this waveform into our formula form. Now let's go find the maximum value for our V out, and so that we can find our low and high cutoff frequencies. I think I'm going to jump to find, or after I found it, and I'll be back in just a second. Okay, so I have gone ahead and found the maximum. You can see here that it kind of stays at this value for a while, and then like 50 and then 60, and now it goes down. So I'd say anywhere within this range, it's about as high as our waveform gets. So I'll say that the maximum our V out is at 30,000 hertz, and it's a peak-to-peak voltage of 5.52. I guess using the measuring feature, we're getting around there too. So good agreement with that respect. So maximum voltage 5.52. Okay, so same as before, our input signal is still at this 105 millivolts peak to peak. So because that's staying constant, I mean, we'll use that to find our gain, but just to find our high and low cutoff frequency, we will take our peak voltage, so 5.52, divided by root 2. So it's going to be at, I keep forgetting that I'm zoomed in, 390. I think 390. That's going to be our voltage, and then I'm going to set my cursors as close to 1.95 and negative 1.195 as possible to kind of get that value. I think overall it will lead to so I guess 1.96 is about as close as I can get, which is fine. Okay, so that means a delta V of 3.92, which is pretty close to our value. Okay, so let's start. Let me zoom out so we can see our function generator. Now we have this kind of queue where, so hopefully you can see that. And I'll read out the value if it's too small to see. So I'm going to start decreasing my frequency until we find a to our cursor lines line up with our peaks. Oh, passed it. So it is once again pretty low. I think the last time it was 1.85 for our minimal. So when our gain was max, or when our gain resistor was maximized, this time I think it's right there. So I think our low cutoff frequency is going to be 2.2 kilohertz, or 2,200 hertz. Okay. Now let's find our high. Start going through. Whoops, what did I do? Oh, I hit the output to the other signal. All right. And then, okay. Let's go ahead and measure it too. That's a pretty good agreement. So we'll call our high cutoff frequency to be 340 kilohertz. So we have slightly narrower band compared to when our gain resistor was at this at its maximal value. So obviously the amplitude has changed for our output signal, but our bandwidth has stayed marginally the same. Okay, so now you can, in the same way, calculate the low cutoff frequency, now using the 468 ohm value for our that resistor, to find that equivalent resistance in equation 13. And you can calculate the gain the two different ways. So one way is just from our ratio. So I'll go ahead and do that one right now. So what was it? We had 5.52 as our maximum output voltage, and then our input voltage is staying the same at a constant 105. So our value is 52.57 for our gain from our ratio of our two signals. And I'll leave calculating it the other way using equation 10 up to you. All right, that concludes part 13. Let's move on to the next one. All right, so now let's move on to step 14, where I've zoomed out so we can see both the function generator and the oscilloscope. Here we are asked to increase the input voltage by 100 millivolts, and we want to see this point at which we start to see our our output signal start to clip. So right now, there's just to measure it, this is the gain is still, or the gain resistor is still set to its minimum value, so we're seeing the maximal amplification of our signal. But now, if we start to increase our small signal from 100 to 200, let's go to 300 millivolts, and I'm adjusting the scale so we can start to see, or so we can see the whole thing. So even now we can start to see that our waveform is starting to bottom out. 500, 600. Okay, so now at this point we can definitely see that our waveform has clipped both at the bottom and at the top. It's clipped both at the peak and the trough. And at this point, since our signal is being distorted, it is no longer considered a small signal. Okay, so we'll say that at 600 millivolts, peak to peak is when both our peak and our trough are being clipped. So what exactly is specifying this window, this range at which our amplified signal can exist? And if we, well, actually I already have the measure tool out, we can see that our peak to peak voltage at this point is 21.4 volts. Let's actually use our cursors too, since we've been using them for this entire lab, and double check that. Channel 2, or let's move this up a little bit. Sure, right there. And then we are going to all right. So our delta V, our peak to peak voltage, is around 21.2 volts, or 20 volts, the value that we set our DC power supply to. So this DC current that we have going through, or this this direct current, this 20 volt current, is what's limiting, it's what's specifying the window in which our signal can be amplified. All right. So this gives a maximum value of what our waveform can be. So when actually measuring it, it's 21.2, but from our power supply, we have it set to 20. Okay, so that is part 14. So in this next part, in part 15, we are asked to short the gain controlling resistor. So the potentiometer, right now it's still at its minimum value of 468 ohms, but let's see if I can turn down the camera so it can show you. If I instead, well, even more, if I instead disconnect this wire and attach this green wire in line with our capacitor, our C3, that'll complete the circuit, So I'll have it up here so you can see what happens when this circuit is reconnected. So let's go, boom. Okay, so you saw the input signal, well, I'm sorry, you saw the output signal get much larger. So this is consistent with what we were seeing. So as the gain resistor was lowered, we saw that the signal was boosted more. And now that the resistance has essentially gone to zero, we see this kind of maximal boosting of our signal. And the clipping is even more pronounced. So now we are asked to decrease our Vin so that our waveform is no longer distorted. All right, so let's just do this. So let's put it back, and we'd start decreasing. So it's still at 600, so let's move it back down to 100, kind of our standard. And this has all been at like 10 kilohertz, just because it's kind of been our standard method, or our standard frequency. So that looks, you can see that channel 2 is still being boosted, or it's still being cut off. So let's go even lower. Okay, so we're down to 60, 50, and okay, so I would say that at 40 millivolts, I guess I can go in even smaller increments. It's kind of hard to say when the distortion truly stops. You can see that it's still kind of slightly lowered. We're kind of seeing like this slight DC offset. But I would say at well, now it really does look like it's, because you can see like the lower half of the waveform is still kind of like slightly peaked. But now at 20 millivolts peak to peak, we are seeing a, it looks like a normal wave. So let's call it 20. And let's try to find our gain. So zooming in, we'll need to measure both of our values. So let's do this. I can't really go any smaller for the channel 1. It's as small as our signal can get, but let's do this. Let's use our cursor, and we'll measure channel 1 first. And then we will move this, and so that's about right. And then move this one. So our peak-to-peak voltage for our interesting. Even this is kind of has a significant offset. I would say our peak-to-peak voltage for our channel 1, or Vn, is 23.2. Yeah, so pretty close to that 20 millivolts. And then our output voltage from our channel 2, let's switch this to different channels. Yes. Let's move our cursors again. Say it's right there. And move this one. So our Vn was 23.2 millivolts, and our output here is 7.08 volts. So if we were to calculate the gain in that case, it is much higher. So we're getting something like 7 over 23 millivolts. Let's see if I can focus. Is 305.2, a gain of 305.2, which is much higher than when we had our minimum value for our resistor. final part, part 16. Here we are asked to replace the coupling capacitor C1. That's the one that we've been using for all of our calculations. It was a 0.01 microfarad or a 10 nanofarad capacitor. And we want to replace this with this 470 picofarad or 0.47 nanofarad capacitor. Hopefully got those conversions right. So let's see if I can show you. Last part that needs to be measured. Not so important that we record this value, but just to show you, it is 0.452 nanofarads or 452 picofarads. So we're going to replace this capacitor in our circuit. So that's going to be this guy right here. So out you go. And in you go. And now we are going to be finding a new low and high cutoff frequencies. Okay, so let me hook this back up and get to our measurements. Okay, so I have gone ahead and found what our maximum value can be. It's around 1.84, going by our cursors. So our output has a maximum output voltage of 1.84, and this is around 100,000 hertz. And if we wanted to find our high and low cutoff, again we can do this quick calculation of dividing our maximum by 1 over root 2. So that's 1.3, and then again adjusting our cursors, so it's that 0.651. Adjusting our cursors so that we can find the bounds. So our max output is this 1.84. Let's go ahead and measure what our input signal is. We'll switch our cursor to channel 1 and kind of bring it down. So previously it was this 23.2 and let's see, this can't get any bigger. Okay, it's a little all over the place. So let's do that, and then this maximum I'm seeing is right there. All right, well, it's around 23.2 still. Maybe it's a tenth of a millivolt difference. Maybe this is slightly up, but so our input signal is still, or say 22.4. Okay, so we can calculate the gain at our maximum. This would be, I guess, 16B, so 1.84 over this 0.0224. And that could be that part. Now let's find our high and low cutoff. So, like I just calculated, it's going to be roughly when we set our cursors to positive and negative 0.65 volts. So let's go ahead and do that. Channel. Actually, we do want channel 2. We can get rid of this. And let's adjust our, so what do we want? Positive 0.65 and negative 0.65. I think 0.652 is going to be our closest value. And now we can start adjusting the frequency until we kind of see this range. Okay, perfect. So now let's, ooh, I autoed it. That's fine. I think my cursor should still be at the same spot. Okay, so let's start decreasing our frequency until we see it coincide with these points. That's pretty close. Let's go and measure it too. 1.3. Okay. So I would say that our I would say that our low cutoff frequency is 21 kilohertz. Measure is pretty close, 3.5. I guess it's closer to 20. Yeah, okay. So I'll say our low cutoff is at 20 kilohertz, or 20,000 hertz. Let's see if we can find the upper one. So let's start increasing our frequency. Okay, getting close. And here we have that we're in like the megahertz range, which is crazy. All right, and we can say that our upper is 1.3 megahertz. All right, that is the rest of our measurements for this part. I think that'll be all.